Okay, so I'm going to try problem 4 in this section of our thermo packet. And what I've noted is that the distance from A to C is smaller than the distance from C to B. So that this location here, PAVA, is a greater value than PCVB. Okay, cool. So let's go through each step and determine the work done on the gas, the change in energy of the gas, the heat added to the gas, and the total process heat, change in energy, and work. So the first thing we can do is think about work. When I think about work, I think about compression. If you compress it, it takes work. So work is negative P delta V. Work is the area under a curve, and if it's compression, it's positive. So let's go ahead and go from A to B first. Ooh, that's a hard one. But I know that the work is going to be negative because you're expanding the gas. See how the volume is getting larger? So we're expanding the gas, which means our work from A to B is negative. Okay, next let's go from B to C. So from B to C, you are compressing the gas. So our work is going to be positive. We are compressing the gas. Okie dokie. Now from C back to A, there is no delta volume. So our work is 0. All right, nice. So the next part of my thinking is going to be about the delta U. Remember that energy just corresponds to temperature. So if the temperature goes up, that means the P times V value goes up, and therefore the energy goes up. Right, so this is just a proportional sign. Okay, proportional to PV. So here, I put some numbers on it just so we have a better scale. So here we have a P times V value of 20, P times V. So that means that our energy is 3/2 PV, or 3/2 20, and then corresponding units. And then at location B, our energy is 3/2 PV, where our PV is 12. So from A to B, our energy, our temperature has decreased because the P times V value has decreased. So delta U, negative. Decrease, T went down. So if T goes down, this is negative, right? And T is the P times V. All right, now from B to C, over here we have a PV value of 12, but at location C, we have a PV value of 2. So again, our system's energy goes down, our temperature goes down, our PV value goes down. From C to A, though, our temperature is going to go back up because we see that the P times V value increases from 2 back up to 20. Okie dokie. So the heat can be added by putting something in cold water or putting in something in boiling water, depending on if you're taking away heat or adding heat. So what we can do there is we can think of how did temperature change, i.e. how did energy change? That happens from work and from heat. So if my work was negative and my delta U is negative, then that's leaving me as unsure about the heat exchange. I don't really know. Was no heat exchanged here? Perhaps this is adiabatic. So I'm going to say 0 heat exchange, adiabatic. Now I just guessed. It actually could be a little bit positive, a little bit negative. A problem would probably tell you that that process is adiabatic if Q is 0. But here, this is just practice, just for us to discuss. All right, so from B to C, we know this process is isobaric. Okay, and the change in total energy was negative, but the work done is positive. So in order for the total change to be negative, if you do some positive work, you have to let out a lot of heat. So negative heat. You have to put that baby in some cold water, shrink it down. And from C to A, we're now doing an isocuric process, isovolumetric, not changing the volume. No work is done, but yet the system's temperature goes up. How do we do that? Well, we have to add heat to do that. So let's look at the total process all together, from A back to A. So is the amount of change in energy like looking at this total column here, this total delta U, what's going on with all of our information. Okay, so this means we are going to have to compare the values of those negatives to that positive, because I want to know if the overall delta U is positive or negative or what. So let's think about total process. So let's think about first the work on the total process. So there is negative work done from A to B, the area here, and there's positive work done from B to C. So when you think about that bottom section in gray just totally cancels itself out. So the only work, the net work being done, is just what we see in blue here, the area inside the processes lines. So the total work is dominated by this top motion here, which is expansion. So the work on the total system is negative. Okie dokie. So net work on a system, just to recap that, net work on a system is the area between all of the lines, and you'll tell if it's positive or negative by what this top line is doing. So if your process is like this one is going clockwise, a clockwise system has negative work on it, always. A counterclockwise system will have positive work. But all you need to do is think about the area inside the processes lines and which process is on the top, whether it's compression or expansion. Remember, compression takes work. Compression is positive work. All right, so let's now think about the next part of it, the delta U. The delta U is the change in temperature, and we're looking at that for the total process. So that means from A back to A, how does the PV value change? Well, at A, P times V is 20, and at A again, P times V is 20. So in this entire process, if you go from the same starting point back to the same starting point, this has to be 0. So then, by your process of elimination, what heat total has been added to the system, the delta U is a combination of work and heat. Work was negative, but the delta U is 0. So a negative plus a positive number is going to come out to be 0. Negative plus positive is 0. So the same amount of heat added as work done for our process. Work is negative, change in energy is 0, heat added is positive for our total process. Let's talk about how to make these processes happen experimentally. So first, let's write down what goes on in each one. So here we have adiabatic expansion. That means our change in temperature decreases. Okay, what are we going to need for that? We're going to need a container, and we're going to need insulation on our container so that there can be no heat exchanged. We're going to need a lid so no molecules can escape. Okay, now my lid is going to be free to move, and what we're going to do is we're going to move lid down, up quickly with all of these conditions. So sealed, insulated container, no heat exchange because we have the insulation on it. Okay, so next step, way to complete B to C. B to C is a process that is isobaric, same pressure, and we are compressing. We're going to take this container here, and we are now going to remove the insulation. Okay, we are going to let the atmosphere act on our rubber stopper, so we're not going to clamp it in place, it's going to be free to move. Notice the number of molecules will remain fixed because the container doesn't have any openings for them to escape. Now, how are we going to get it to compress down? Well, let's take a tub of ice water, and we will take our ice water tub, and we'll put our container in that tub. Bam. Next step, from C to A, let's check it out. So that's isovolumetric. So we're going to write that down. isovolumetric, and we have a pressure increase, which corresponds to a temperature increase. Okay, so what are we going to do now? So let's take that same container here, like this, and we will clamp the lid down. So let's get rid of this concept that it's free to slide. It can't be free to slide because we have to keep the volume constant. So let's take this clamp right here and clamp our lid down so the lid motion is fixed. Okay, and then we want to increase the pressure and temperature. So now let's go ahead and take that and we'll put it into some really, really hot water that has been on the stove. Hot, hot, hot. So let's take our container and we'll put it in a hot water bath. The following pages have more of these problems that I suggest you try.